Let's talk about function notation now that we have a little bit of a better idea in terms of how functions work. So if we're dealing with the coordinate plane, we tend to organize ordered pairs as being in x, y. But as we saw in function notation, we can now call ordered pairs x and f of x. So the x's stay the same, they're pretty much constant, but anytime we see a y, we can replace, like we see over here, we can replace that y with the term f of x. For example, if we have the function y is equal to 2x minus 7, if I wanted to write that in function notation, I would call that f of x is equal to 2x minus 7. Or if I saw something in the form y is equal to 3x squared minus 5x plus 1, in function notation, I would just call that f of x equals 3x squared minus 5x plus 1. The x and y are kind of random. We don't have to use x and y, so we use x and y's over here. We tend to use x and y's when we're looking at coordinate values, but I don't necessarily have to call that f of x equals 3x squared minus 5x plus 1. I could also call it something like g of a is equal to 3a squared minus 5a plus 1. And then if we're looking at ordered pairs, our x value would be represented by the a value, and the y value would be represented by the g of. So anytime you see that of notation, we're pretty much dealing with the y values. Let's talk about how we can evaluate functions based on this information. So let's go back to that original y is equal to 2x minus 7. With the understanding, again, that I could also call that f of x is equal to 2x minus 7. 2x minus 7. Okay, so let's evaluate f of, let's say, 5. Okay, so if I ask you to evaluate f of 5, what that means is every time I see an x in that function, I'm going to ask that you replace that x with the number 5. So what we're doing is we're inputting into that function the number 5 every time I see an x. So let's do that. So let's take this function and let's substitute in. I'm going to keep it in red to be consistent so you can see how it works. We're going to substitute in a 5 for x minus 7. Sorry, it should look a little bit more like a times. It's 2 times 5 minus 7. So f of 5 is equal to 2 times 5 minus 7. That's the same thing as saying 10 minus 7. And that's the same thing as saying 3. So f of 5 equals 3 is telling us that when we have an x value of 5, so we input a 5 for x, we have an output value or a y value of 3. That's also giving us an ordered pair that's on this graph. So if we were to graph this line, the ordered pair of 5, 3 would be one of those points on the line. Let's do 1 or 2 more examples of this. Let's go back to f of x is equal to 2x minus 7. Let's find f of negative 1/2. And again, what we're doing is every time I see an x, I want to substitute in a negative 1/2 for that x. And then we're going to simplify it as much as we possibly can. 2 times negative 1/2 is negative 2 over 2 minus 7. That gives us negative 1 minus 7, which is negative 8. And so that's telling us when x is negative 1/2, y is negative 8. So we have another ordered pair that's on here. And another way to write that using function notation is f of negative 1/2 is equal to negative 8. Let's do one more, evaluate, and we're going to use that same function as we have above. So let's evaluate f of 3a minus 1. All we're going to do is every time we see an x, we're going to replace that x. And let me just, again, I'll make this red to make sure that you can see it. We're going to replace that x with 3a minus 1. So substituting in, we have 2 times x. Again, instead of calling that x, we're going to call that 2 times 3a minus 1. And then don't forget our minus 7. Using the distributive property, we get 6a minus 2 minus 7. And that's the same thing as saying 6a minus 9. So that f of 3a minus 1 is equivalent to saying 6a minus 9.